everyone. My name's Patrick Hulin. As Brendan said, I work at MIT Lincoln Laboratory, which is sort of MIT's mostly DoD-funded lab. So we work on problems that are relevant to sort of government applications, and obviously security and reverse engineering are really important parts of that. So one of the problems that we face a lot is we need to reverse engineer sort of hard targets. So I'm going to start by talking a little bit about what the Panda system that Brendan mentioned is and what we're using it for. So my group has been developing this Panda system. It's a reverse engineering tool. The basic way it works is you are supposed to, it has a deterministic record and replay system, which means that you can collect a recording of system execution and replay it exactly. And then you can instrument that recording and try and build up knowledge about how it works. So this talk's going to start out a little bit with a case study and what can happen when you don't do some of the sort of best practices things that Mike mentioned in his last talk when you're trying to build open source security tools. So Panda is a fork of QEMU, which is an open source emulator that probably a lot of you have used in some capacity. It's really become a pretty integral part of a lot of security projects because it implements a bunch of different architectures in a unified way and with high enough fidelity to actually run real operating systems on them. So when we first developed Panda, we based it off of QEMU 1.0.1, which was a version of QEMU that was released in, I think, late 2011 or maybe early 2012. So that was obviously, at this point, was a long time ago, though at the time, we didn't think that QEMU was going to change that much over the next few years. It actually changed a lot. So it turns out that open source projects, especially ones that get a lot of use, move very quickly. And if you're working on a fork and you don't really coordinate with the main developers, you can very quickly have your forked code diverge quite a lot from the source project that you forked from. So when we decided that we really needed to start keeping up with modern QEMU changes, because there were a bunch of features that we wanted in Panda. We wanted the ability to run Mac OS X, which only runs in modern versions of QEMU. We wanted some of their sort of new instruction set support in x86, and a few other just sort of general performance improvements. We faced this sort of very difficult task where we thought it was going to be very hard to port our record replay system that we had built and was a key feature of the original version of Panda. And I'm going to talk about why that's so hard in a second. But we wanted to figure out a way to make that easier. So just for a bit of background, I want to talk a little bit more about how Panda works. So as I said, it's reverse engineering via dynamic analysis. So the sort of way you use Panda is you have to find a way to trigger the behavior that you're interested in reverse engineering, and then you can watch that behavior and instrument it at various levels. So we have like a dynamic taint analysis, we have a bunch of a dynamic slicer, we have a bunch of other different like miscellaneous analyses that you can use to instrument that recording and figure out what happened. So one of the reasons that we want record replay is it means that you can run, do reverse engineering in a dynamic way with a really heavyweight analysis. So once you record a segment of execution at near normal execution speed, you can then run an analysis with 50 times or 100 times overhead and not worry too much about the fact that you would normally have to wait for like 10 minutes to click the next button in Google Chrome. That's not something that we want to do. Another key feature that Panda has had, and although we haven't actually ported this yet, is it's architecture independent. So you can do things like support Android. We haven't ported the specific Android support, but the architecture independent quality is still there. So just to give a summary, the way I use it is I record a sort of segment of execution, and because we're using an emulator, we can record a whole system, which means we can reverse engineer operating systems, which is a pretty key feature. And then you sort of write these analysis plugins and over run the replay and analyze it and slowly understand what happened. So that's sort of the high-level summary of how Panda works. I'm going to dive now into record replay and talk a little bit about why that was such a hard thing to port forward. So you want to record a segment of a computer executing, what do you need to record? So first off, the first kind of insight that we had was that the vast majority of instructions that a computer executes, that the CPU executes, are deterministic. If the RAM contents and the registers are the same, that instruction will have the same result every time. Now, there are a bunch of exceptions to this. In particular, any time that the CPU has to do input or output or interact with the outside world in any way, you need to be able to reproduce that result exactly in order to create in order to cause the CPU to follow the same execution path. So conceptually, you can think of this as drawing this circle around the CPU and RAM and saying this is a boundary, and anything that crosses this boundary, so anything from outside the CPU and RAM that impacts the execution of the CPU and RAM. So that could be instructions that have non-deterministic effects like RDTSC, which will execute differently depending on the state at the beginning of execution. Or it could be an interrupt. Obviously, that's something that could mean something is actually happening in the outside world, or it could just be the CPU saying, okay, the timer's gone off. Time to stop execution and figure out certain things. Or it could be DMA coming in for a device. And these are just a couple examples. These are the most prominent ones, the ones that most frequently occur. There are a couple other ways that stuff like this can happen, but these are the main ones. These are the main things that would cause a replay to do something different if you just started with the same contents of CPU registers and RAM. So the way this fails, the way the system can fail, is if you fail to record one of these things that's crossing this boundary. So if say you have a device that uses a QEMU API, so QEMU has all these virtual devices which are sort of analogs of physical devices but implemented in software. So like a virtual serial port, a virtual hard drive, a virtual network card. So these devices use QEMU's internal APIs to do things like reading and writing from memory and sending interrupts. So the way you would implement record replay in QEMU is you would say, okay, where are the APIs that devices can use to do this kind of behavior? And let's place instrumentation at those API boundaries to capture whenever one of these changes happens. So unfortunately, the QEMU has this big and sprawling device code base, which is there's just a lot of stuff going on, and many of the devices don't actually use the APIs in the way they're supposed to. They don't quite follow the contract. So as a result, you'll end up with rogue devices that will write to memory during the recording step, and then you won't replay that memory write during the replay step, so your replay will do something different because the contents of memory have now diverged. They're different at a certain point in the replay. So when we started porting the record replay system over from QEMU 1.0.1, which the original Panda was based on, to new QEMU, which is now version 2.0.7 or 2.7.0, we initially faced this huge number of record replay bugs because all of these APIs had changed and we needed to re-implement our instrumentation in completely different places. So one of the problems with debugging QEMU is that it's very state-driven. I mean, just like a real computer, at any point, the next state in QEMU is dependent on the previous state, and state changes can get kind of stashed away in memory, just as, again, on a sort of real physical computer, and then not influence execution for a long time. So the cause of the thing that eventually causes the replay to go off the rails, like that device write, might not actually cause a problem for many, many, many basic blocks. So let's just think about an example. So as I was saying before, let's say that a device writes guest memory and we don't record it. So what that will cause is the guest OS will eventually follow a different execution path whenever it looks at the result of what that operation was. So as we record and replay, we need to deliver interrupts in exactly the same way as we did the first time in order to keep the replay in lockstep with the recording. So we keep a very precise source of timing, which is just counting guest instructions. But the problem is that if the guest OS ever follows a different path, this disrupts the lockstep timing, and now we're not reproducing the original execution exactly, and we can't deliver interrupts on the boundaries. Now, for sort of recording size reasons, we only record, as I said before, we only record that non-deterministic stuff. So the only sort of checkpoints we have to see timing are when something non-deterministic happens. So when an error changes guessed execution, we often won't see it until the next replay checkpoint, which could be much later, which could be hundreds of thousands of instructions later. So this is a problem, and it means that bugs take forever to manifest. So at this point, I was asking myself the question, how can we debug more efficiently? Like, what can we do that'll make our debugging easier? So I just posted a snippet here from a team, a 2004 paper from a team that made a system called Revert that was also a record replay system. They had I don't know if it's clear on the screen, but it says the Revert team analyzed a replay divergence bug caused by the order of page fault exceptions that took 2 months to find. So that's an idea of how long it can take traditionally to find these bugs. These are kind of the worst of the worst in terms of debugging. So let's go to. I'm going to talk a little bit here about what I mean by debugging. I know you guys probably all have a concept of what this means to you, but I just want to get some unified terms here. So by a bug, I just mean that a program produces wrong output for a given input. I mean that seems like a pretty uncontroversial definition, but when you're a programmer and you want to fix a bug in your code, usually my first step at least is to start by staring at the output and trying to just think very hard, like what could have caused this output. Then maybe I'll find the code that produced that output and try and understand why that code executed. But sometimes this can lead to a very long process of following back causes of events in the program. So when you first start debugging, you find an immediate program state, like a particular line of code that executed a printf statement, that a printf function call that caused some output that the program produced. But this might be guarded by an if statement, and the if statement is testing some condition that was set a long time ago in the program, and now your debugging task is no longer why did the program produce this output, it's why did this condition get set. And sometimes that condition will have been set because some other condition was set, and you need to follow that second condition backwards. So that you can view this as kind of a series of state transitions of the program, and you're trying to follow a cause-effect chain backwards to find the first cause, the first place where the program sort of deviated from your idea of what the program was supposed to do. So I've got kind of a graphical example on the screen here. So say you have a program that sets a equals some variable named a to 1, executes a bunch of unrelated code, then checks if a equals 1 and sets b equal to 0 or 1 depending, executes a bunch of unrelated code, and then says if b equals 1, then trigger some bug like an assertion failure or something, and otherwise set c equals 1 and continue executing. So in this case, if you just ran this program and saw the output bug, like saw the assertion failure or something, you have to follow a couple steps back in this cause-effect chain to get to the root cause, which is that a is getting set equal to 1 at the top. And that's a lot of code. And one of the real problems here is that debuggers work forwards, whereas the task that you're trying to do when you're debugging, especially in a really state-driven environment, is a very backwards task. So you're trying to figure out the causes that preceded these effects, whereas debuggers, once you get to the bug, they can't go forward anymore. You can only kind of examine the state of the program. You can't run backwards and step through the conditions. So I'll talk about what our solution to that in a second, but let's talk a little bit more about sort of traditional approaches to debugging. So again, as I was saying, debuggers allow you to find state transitions primarily through things like stepping through code, setting wash points, that kind of stuff, and they work forwards, and we're trying to trace backwards. So there's kind of a traditional sort of debugging or regression prevention approach is unit tests, where the goal is to kind of split program into components and compare against known good behavior. So like, you'd call one function or one module of a program and check that its behavior is good. So here, just to connect back to the Panda example, if you're doing if you're trying to build a record replay system, we know what the good behavior is. So if we can build a system that enables us to compare directly against compare the replay step state directly against the record step state, then we're gonna be able to find the place where it diverged, and I'll get exactly into how we're gonna do that in a second. I wanted to start with kind of this. We're gonna look at this pretty abstractly, but there's sort of this more modern idea of git bisect, which is sort of a source level binary search to find the first bad version of a program. So if you're not familiar with git bisect, the way it works is you create some test case that demonstrates for a given version of your source code whether or not there's a bug. And so you run git bisect. It takes you give it the first good and first bad version, last bad version that you know of, the last good and first bad version that you know of, and then it goes to the middle, executes tests, says if this is good, marks that version as good, and updates the bounds, and does a binary search over, in this case 4 tests. So I want to extend that binary search idea and see if we can use it to find a location in the cause-effect chain where the first error occurred. So yeah, git bisect isn't perfect. It can find a set of changes, but they can be big and complicated, and we don't have unit tests on Panda, and that's our fault for just not being quite smart enough. So as I said, we're going to continue the binary search idea and find the first bad state over execution, and hopefully that first bad state is going to be the root cause in a sense. I mean, these are kind of abstract terms. Often the record replay bugs are caused by like some fairly complicated set of circumstances. So what we need to make this work is we need a source of timing in the record replay system, like git bisect's commit hash is kind of the source of timing that they use. That's the thing that you're doing the binary search over. In a traditional binary search, it would be the array index. And we need an internal consistency check with like the git bisect test case, which in our case can just be comparing record state against replay state. So let's look at this in detail. So the way we can do this is we can, if we have some way of checking at different points in the recording and the replay whether the state is consistent, then we notionally could just do a binary search over time and find the first place where the state diverged. So that should just work as long as we can come up with that system that will allow us to go back and forth in time. So the kind of insight that I had here working with Brendan is that you can use a second record replay system to debug a first. So in this case, we can use a system called Mozilla RR, which is developed by a bunch of people at Mozilla, a couple of whom have now left. But the idea is it's a user space record replay system, and we can run QEMU, which is entirely runs in user space, inside RR, record QEMU's recording step, and then record QEMU's replay step. Record Panda's recording step and Panda's replay step, and then replay both of them and check different points in time to do a binary search over where the first divergence was. So if there's one thing to take away from this presentation for your own debugging techniques, it's that Mozilla RR is an amazing tool, and you should absolutely be using it all over the place. It makes debugging much more pleasant. Because of exactly that thing that I talked about at the beginning, that debugging really is more of a backwards process than a forwards process. So how do we implement this? So as you can see here, we've got some kind of notional tool stacks, but on the left we have the first 2 recording steps in RR, and on the right we have the replay steps in which we replay the recording step of Panda and the replay step of Panda. So and we built a custom Python script which is not online yet, but will be very soon. That drives that recording process. So the problem with the sort of engineering details here is that RR can be very slow when operating on large traces. So it's difficult to precisely jump to a specific guest instruction count. So we implemented this kind of multi-step synchronization process where you can use RR has this internal event timer that it's much easier to jump to, so you can kind of use RR's internal event timing to quickly jump to somewhere you think is in the neighborhood of the point you want to be for doing one of those tests of state consistency. And then you can sort of set a conditional breakpoint that tries to get you to exactly the guessed instruction count that you want, which is sort of as a reminder, is the internal source of timing that we're going to use to synchronize the record step and the replay step and make sure that their state is consistent. And then finally, you can use a conditional breakpoint on basic block execution to synchronize the sessions exactly, to get them to exactly the same point in the record step and the replay step. And then you can take the CRC32 of memory and compare, and if they're the same, you mark the instruction count as good, and otherwise you mark the instruction count as bad. So just to go back to the example here, so each of these, the record and replay step both have precise instruction counting the whole way. So if you get the record step and the replay step to the same instruction count, they should have the same state. And so here, the red part of the replay step is saying, okay, that's where the states diverged. And so at that point, the memory should be different. And so if we can find exactly that point where the memory diverged, that's going to be the cause of our failure. So once you find that exact point of failure, it's not quite right, because often the failure will be in device code and won't give you exactly the point where the failure occurred. But we can do something we can kind of extend this idea and do a binary search over the guessed memory contents in terms of space. So we can divide the guessed memory into two halves, check both halves, and whichever half differs, we can then continue to compare until we find the exact memory locations that differ between the record step and the replay step. Once we find those, we can then use Mozilla RR to set a watch point on the guessed memory location that changed. And then we can use RR to execute backwards and find the most recent change that occurred to that guessed memory location. So once you do that, that will just give you exactly a backtrace of the code that caused the first state diversion. And that's pretty cool, because it means that this entire process that I've described is entirely automatable. So if you can record the recording step and record the replay step, you can then just run this script, and it will automatically find the first divergence between these two sequences. Between these two execution traces. So that's really useful, and that's kind of a key thing that has helped us in this process of sort of rectifying our mistake of not keeping our code up to date with QEMU over the past 4 years. So I just wanted to give a little bit of a summary and our kind of lessons that we took away from this. The first one is binary search is useful more often than you think. This technique is pretty specific to this use case, but it can be used in any case where you have kind of a canonical, a good internal consistency check for a program and a source of timing, and that source of timing could be a file pointer. Those tend to be sort of monotonically increasing over a life of a program. It could be any kind of counter. These kinds of things can provide consistent sources of timing. RR, as I said, is basically an infinitely better version of GDB, and I highly recommend using it for debugging. It's incredibly useful. And using record replay systems for debugging other record replay systems works very well, not super surprisingly. The last point that I wanted to make is that automated debugging techniques, even for one-off tasks like this, which is where it's kind of we expect to use it maybe 5 or 6 times, can be really worth the effort if you see sort of similar bugs. Because in this case, the record replay bugs manifest basically the same way every time, which is there's a state corruption very early in a recording, and then the replay fails maybe a million instructions later. And so that cause-effect chain was always very hard for us to walk back, and used to take us many, many days to debug. And this script took like 2 days, 3 days to write, and now it just finds all those bugs automatically, which is really great. Okay, that's all I had. I wanted to thank Brendan, and thanks to also all the other Panda devs and open source contributors. If you have questions about Panda or about this technique, please feel free to talk to me after or ask now.
Okay, let's thank the speaker first. And then see if anyone has questions. Okay, so one that I'd like to start off with maybe is, you know, So since we're at an open source workshop, we have lots of, very talented people here in the audience. What sorts of things would you like to see as sort of contributions to Panda?
Great. I would love it if someone would figure out how to get a symbolic execution engine doing sort of symbolic execution in Panda. I would love it if we had a Python plugin system. That would be really cool. Currently, all the plugins are in C or C++. I don't know. Yeah, I would love it if we had a better GDB interface. If you could use, if you could hook up GDB to QEMU and then use similarly to the way RR works. If you could then reverse continue on a whole system, that would be really neat and a really great way to sort of examine very closely what particular pieces of code we're doing.
Okay, so one thing that you mentioned is that there was really sort of a lot of pain involved in going from an older version of QEMU to a newer version of QEMU. So I guess do you have more maybe general advice on how to keep synchronized with an external project that you depend on?
I think part of that is it really helps if you can coordinate. One of the sad things about Panda is it's tough for us to coordinate with QEMU because they're moving so fast. And their needs are fundamentally different from ours. They're mostly focused on like sort of industrial scale, like cloud setups where you have a million people running in a million virtual machines running in hardware virtualization mode, whereas we're using QEMU's like emulation mode, which is fundamentally different. The other thing is that you just kind of need to be disciplined and like pull in changes frequently. It's kind of our fault for not doing that. I mean, you just need to actually, if you want to get the new features that come out in 2 years, even if there are no features that you need now, it's a lot easier to pull in changes incrementally and fix any bugs that come up than pull in changes and have this giant merge conflict where you have like 100 places that you need to fix merge conflicts, and it takes a week to get it to compile. It's much better to be a little disciplined in the first place.
These are just idle Panda questions, but are you worried that the emulation mode will go away with QEMU, with more and more of their like large deployments using the VTX type instructions? And then as Panda matures, how close in capability does it become to something like Symix that's pretty expensive, but gives you the sort of forward and backward ability to instrument a system? So those are two unrelated questions. But
sure, I'll start by saying I'm not super familiar with Symix and exactly what it can do. As I understand, it's mostly like an embedded device emulation platform. We have been thinking a lot about how to get embedded devices, since theoretically QEMU is a whole system emulator. Most embedded devices, if you just had the virtual hardware implemented, whatever specific to that device, then you could run it in Panda, do record, replay, all this cool stuff. Unfortunately, it's not actually that easy. Getting the virtual hardware implemented is really hard because these things are often private or whatever, or they're very one-off. So that's something we've been thinking a lot about. We would love, if you have ideas about that, we'd love to hear them. To address your first question, I think that there are definitely enough of QEMU's core developers who are interested in the emulated mode. I don't know why. I think they mostly work for Red Hat. I don't know why they care, but they have definitely been working on it. So they've been making some major improvements over the past 6 months, which has made it even more difficult to keep up. But it seems like it's not going away anytime soon.
Okay, do you have any more questions? All right, then let's thank Patrick again while we get the next talk ready.
Great, thank you.